Hi everyone, so welcome to Turbo Machines, and we are in module number 3, and this is the fifth video I'm doing here on this module, and this is impulse and reaction steam turbines. And in this video we are going to study this reaction turbine and work output and degree of reaction. So far we have seen how that things went on impulse turbine, and how the compounding is done, different types of compoundings and all. So we have seen in the impulse turbine. Now coming to this reaction turbine, so what are the things that we come across in the reaction and work output and degree of reaction. So first and foremost, before entering into this reaction turbine, so what we have seen in the hydraulic turbines, the same thing will be applicable over here. So reaction, why it is called as a reaction turbine is because the turbine blades, moving blades rotate with the help of the reaction of these fixed blades. So steam enters through the fixed blades and and it will come and hit the moving blades, and because of that particular reaction, so the moving blade rotates. So that is why it is called as a reaction turbine. So we will see in the slide what is that reaction turbine in a deeper way. So the turbine in which steam pressure decreases gradually while expanding through the moving blades as well as the fixed blades is known as a reaction turbine. So this what happens is, while expanding through moving blades as well as the fixed blades is known as a reaction. So it consists of large number of stages. So we have in this reaction turbine, number of stages will be there. So it will have a set of fixed blades will be there, and then it will have a set of moving blades will be there. Okay, so heat drop takes place throughout in both fixed and moving blades. Everywhere the heat drop takes place. And then pressure velocity compounding, the same way what we have seen in impulse turbine, the same way. So pressure velocity compounding, here no nozzles are provided in reaction turbine, whereas in the case of impulse turbine, so in the first stage, so there will be a nozzle, so through nozzle steam comes out, whereas in the case of reaction turbine there will be no nozzles provided. Why it is? Because no, in the nozzles are replaced by stators, or nozzles are replaced by fixed blades. So fixed blade will act as a nozzle here. So in which velocity of steam increased over there, and direct the steam enter into the ring of moving blades. Now as pressure drop takes place both in fixed and moving blades, all blades are nozzle shaped. So everywhere all fixed, so there will be there will not be nozzle. Nozzles are replaced by fixed blades, and fixed blades, the shape of the fixed blades will be similar to that of nozzles. And now, so the example of this what you call the reaction turbine is a Parsons turbine, Parsons reaction turbine, because it is named after Parson. So that's why it is called as a Parsons reaction turbine. The steam expands while flowing over the moving blades and thus gives reaction to the moving blades. Hence it is called as reaction. Why it is called as a reaction? As I explained, as I told, so it enters into the moving blades, the reaction given by the fixed blades. That is why it is called as a reaction turbine. So fixed blades are attached to the casing, whereas moving blades are fixed with the rotor. This already we have seen in the impulse turbine also. So fixed turbines will always be attached to the casing, and moving blades will be attached to the rotor. Now coming to this, we will see what is the work output. So as we have already studied about this work done per kg of steam in the stage is equal to u into, that is linear velocity u into Vw1 plus or minus Vw2 Newton meters. So here we can take it as a plus, or you can take it as a minus, because so it is in the same direction, it is a minus, and it is opposite direction, it will be taken as plus. And u is the linear velocity or peripheral velocity. Okay, so the work done per kg of steam, per kg in the sense here mass comes into picture. Per kg of steam in the cage in the stage is equal to m into mass flow rate, because m is nothing but mass of steam flowing over blades in kg per seconds. So m into u, Vw1 plus Vw2, that is Newton meter per second. This Newton meter per second is also called as watts. So then power developed, if you can easily find out what is the power, m into u, Vw1 plus Vw2 divided by 1000 will give you in kilowatts. That is the power developed. And then efficiency. So efficiency is all about output by input. So here output is work done per kg of steam in the stage divided by what is the input we are giving heat energy. The steam will possess some amount of heat. So that is the energy which will be given. That is, and heat is nothing but enthalpy. So enthalpy input is nothing but enthalpy drop in the stage per pair. So then efficiency is equal to U into VW1 plus VW2 divided by 1000 into enthalpy is nothing but H, where H is equal to enthalpy drop in the stage per pair in kilojoules per kg. So this is the efficiency. Now next let us see what is the degree of reaction. If we have seen the same thing in the module number 2, so where the degree of reaction, the definition it will be same here. Degree of reaction is defined as the ratio of isentropic heat drop in the moving blades to the isentropic heat drop in the entire stage of reaction turbine. So it is denoted by the letter R. So R is equal to enthalpy drop in moving blade divided by enthalpy drop in the stage. That is equal to dH2 divided by dH1 plus dH2. That is the ratio of, in a simple term, what we can say is enthalpy drop in the moving blade divided by enthalpy drop, overall enthalpy drop. That is dH1 plus dH2. So here it is given dH1, dH2 enthalpy drop in the fixed blade per kg of steam. dH2 is enthalpy drop in the moving blade per kg of steam. So here V1 square minus V2 square divided by 2, that is kilojoules per kg, or it can be written as H1 minus H2. Enthalpy drop in the moving blade is VR2 square minus VR1 square divided by 2, that is kilojoules per kg, that is H2 minus H3. So next, work done. So some of the assumptions that we have to consider here. So what are the assumptions for maximum efficiency? The degree of reaction, if degree of reaction R is equal to 50% or 0.5, then what we have to consider is alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. That already we have seen in the previous module. So the fixed and moving blades are symmetrical. If fixed and moving blades are symmetrical, then V1 is equal to VR2 and V2 is equal to VR1. This already we know. The kinetic energy supplied to the fixed blade per kg of steam is nothing but kinetic energy is equal to V1 square by 2. So kinetic energy of the energy supplied to moving blade per kg of steam is nothing but VR2 square minus VR1 square divided by 2. So total energy supplied in the stage per kg of steam is nothing but V1 square by 2 plus VR2 square minus VR1 square divided by 2. So total energy supplied per kg already we know that we have seen here. Now the blades are symmetrical. What are the conditions that we have taken? V1 is equal to VR2 and V2 is equal to VR1. So from velocity triangles we will get the VR1 square formula. So therefore total energy supplied per kg of steam is nothing but V1 square minus the entire value, that formula will come, V1 square, all these things. So next, work done per kg of steam is given by work done U is equal to VW1 plus VW2. So U into, so we will elaborate and write instead of VW1 and VW2. So finally you will get U into 2V1 cos alpha 1 minus U, since alpha 1 is equal to beta 2 and V1 is equal to VR2. So next, diagram efficiency or blade efficiency, that is equal to work done per kg of steam divided by total energy supplied per kg of steam. Already we have found out what is the work done, that is U into 2V1 cos alpha 1 minus U divided by total energy supplied, that already we have seen V1 square minus V1 square plus U square minus 2V1 U cos alpha 1 divided by 2. So if you simplify, you will get 2U into 2V1 cos alpha 1 minus U divided by V1 square minus U square plus 2 into V1U into cos alpha 1. Again, if you simplify this, 2U into 2V1 cos alpha 1 minus U, the same thing first we will write. And then, so what we are going to do, we will take common in the numerator, 2U V1 will take common. So finally what we will get is 2 cos alpha 1 minus, we have taken V1 as common, so U into V1. So divided by, in the denominator what we are going to do is V1 square will take common. So then into 1 minus U square minus V1 square plus 2 into U by V1 minus cos alpha 1. So then 2 into U by V1 into 2 cos alpha 1 minus U by V1 divided by, so what we are going to do is, so v1 square, in that v1 gets cancelled, so finally v1 minus u square by v1 square, same thing will remain in the denominator, 2 minus u by v1 minus cos alpha 1. So finally, this diagram efficiency is equal to 2 rho into 2 cos alpha 1 minus rho divided by 1 minus rho square plus 2 into rho minus cos alpha 1, where rho is equal to u by v1, that is equal to blade speed ratio. Blade speed ratio is taken as a rho here. Now coming to this maximum efficiency. To get maximum efficiency, what you are supposed to do is, we should derivate the equation. So whatever the equation that we get, if you derivate it, so we'll get the maximum efficiency. So efficiency is maximum when the term 1 minus rho square plus 2 into rho cos alpha 1 is minimum, or when d efficiency of diagram efficiency by d rho is equal to 0. If it is equal to 0, then we'll get the maximum efficiency. So we will put that diagram efficiency and we make equal to 0. So if you derivate it, so you'll get minus 2 rho plus 2 cos alpha 1, that is equal to 0. So finally rho is equal to cos alpha 1. So therefore efficiency is maximum when rho is equal to cos alpha. Whenever rho is equal to cos alpha 1, then efficiency will be maximum. So same thing if you substitute in the main equation. So maximum diagram efficiency is equal to finally 2 cos square alpha 1 divided by 1 plus cos square alpha 1 will be the maximum efficiency, that is the maximum diagram efficiency. So this is how to calculate or to derive the maximum efficiency of steam turbine. Steam turbine, that reaction turbine maximum efficiency is derived in this way. So thank you for watching this video.